Well, hello. This is the first, I think, of three videos for chapter 3.4. 3.4 will be the last section we'll be doing in chapter 3. We're skipping 3.5. So here we are. There are actually two big parts to this section. One is, in effect, clearing fractions, although it's a little more complicated, or will be. The second part is what's called radical equations, solving radical equations. I think three videos will do the job, a little shorter than some of the other sections. So our first problem example here is, as I have it here, we're going to solve for x, and it's 1/4 plus 1/5 equals 1 over x. And we're going to clear fractions, which means, as we've done before, you can get the common multiple of the denominators by just multiplying them. And so 4 times 5 times x, which equals 20x, is the common multiple of the denominators. You multiply both sides of the equation by that common multiple, that is by 20x, which I've done in green. Uh, there's a distribution involved here, which I've indicated in the next line. 20x times the 1/4, 20x times the 1/5, and on the right side it's not really distribution, it's just multiplication, which I've just left there. And the next thing you can do, and that's the whole point, is to be able to cancel common factors, so that we end up with a line, an equation that has only integers, no fractions whatsoever. And you just solve for x on that basis, which here it's 20 over 9. Now, what I'm doing in all these problems, for clarity, is to check the answer. That is, to put 20 over 9 in this example back into the original equation, which was as given. X will be 20 over 9. And then when I do it a little differently than the textbook does, I have an equation with a question mark on top of it, indicating that I'm trying to find out, to test whether the left side equals the right side. And after a little bit of work, it turns out, yes, indeed, in this example it does. So this is all good. The answer is good. Okay, so let's see. I hope that was an accessible first example of clearing fractions. Here comes a slightly more complicated example right here. So here we're starting off with x plus 1 divided by 3 minus x minus 1 divided by 2 equals 1. The a common multiple that's useful is 3 times 2, or 6. If you chose 12 or 18, 108, I think, yes, you can do that if you want to be funny. It's just not necessary to choose large numbers. 6 does the job, and I'm multiplying 6 by both sides in green, distributing the 6, which is happening right here. Notice the parentheses. That is crucial, and that's why I consider this kind of like a later type of problem. And in our ordering, it's number 2, because you have to add in these parentheses. You must add them in. It's not even an option. And with that in mind, you can cancel 6 over 3 and 6 over 2, which is where you get your 2 and 3 from. Distribute, solve for x. Really that straightforward. And with x equals -1, I'm going to take that -1, put it back in the original equation to make sure left and right side balances out, and sure enough it does, so everything is beautiful. Okay. Now in the first two examples, I think that we go to the third example here, and we'll see. The third example is actually more like the first one than I originally thought, but has a little more complexity to it. The first example also had an x in the denominator there, so this one just looked a little more complicated, and I wanted to have a case where we went through it. Anyway, so we have 1/2 plus 2 over x equals 1/3 plus 3 over x. Find the common multiple. We have 2, 3, and x, so we just multiply that all together. 6x will do the job. Multiply both sides by 6x, which I've indicated in green. Distribute, as I've done in this line, and then cancel out common factors. If you've done your job right, you should come to a line that consists only of integer coefficients, or just integers, and we have. solve for x, and then testing this to make sure the x equals 6 actually works. In case you're wondering, yes, we will say examples later on where the answer we find, we've done the algebra right, but it just turns out it does not, in fact, work in the original equation, and therefore the solution has to be tossed out. So that's coming. And so I'm just playing it safe, checking my work, and you just go down doing the arithmetic, and the last step is, aha, left side equals right side, so this is all good, and that takes care of this problem. The final example in this video will be number 4 right here. And it's a little funny looking, I suppose, and that's why I wanted to include it. In this example, the denominator on both sides is the same. So, no real special common multiple type of idea is really necessary. You simply multiply both sides by that same denominator, which I've done in green. So having done that, which is something a little different here, is we end up with the x plus 4's cancel on both sides. We're left with x squared equals 16. Recall this principle of the square roots. I think it was called the square root principle. X squared equals 16 will necessitate that x equals positive or negative 4. We have 2 solutions, and both of those have to be checked. And notice that when I checked 4 as a solution on the left side, that works out. That gives us 2 equals 2, and that's true. On the right side, however, something very different happens. If we put in negative 4 for x, we end up with 16 divided by 0, and that's no good. 16 over 0 is not a number. It's gibberish, literally undefined nonsense. So it, meaning negative 4 as a solution, has to be thrown out, and that's why I X'd it out. If you had observed earlier that negative 4, when put in the denominator, would give you 0, if you'd seen that earlier, great. That's all to the good. Negative 4 has to be thrown out. Okay, so I think that will address some of the more straightforward examples. Notice that even up to these first 4, we really did have to test these answers. It's a good policy anyway, but we'll get into situations where not all the solutions we got through the algebra are going to work. So that's just the way it works. Okay, so on to the next video. Thanks.